Welcome to the ProMax BRE 600 LNG Processing Tuesday webinar. Today's Tuesday Lunch and Learn is going to be about LNG processing, and what we're going to be specifically discussing today is liquefaction. And the idea today is to just give you a very brief overview of LNG and show you what's possible in ProMax. And we're going to look at a couple of different processes. Today, I kind of briefly mentioned the agenda on the introduction slide, but what we're going to do is we're not going to assume that you have really very much prior knowledge about LNG or liquefied natural gas. So we're going to talk about LNG, what it is, what the motivation for it is, and then I'm just going to show you three different liquefaction processes in ProMax. We're going to take a look at a multi-stage cascade liquefaction process, a nitrogen liquefaction process, and a mixed refrigerant liquefaction process. So just to get us started, let's talk about the motivation for LNG. Why would we want to liquefy natural gas? The idea here is that gas is a very good energy source, right? It's clean, it has a much lower carbon footprint than, say, coal. The problem is it's not very dense. I mean, it's a gas, right? And so it's difficult to transport. If you want to transport gas around and use it as a fuel, you need something like a pipeline to put it in and deliver it to consumers. And in many places, there's simply not a pipeline that you can put gas into if you have gas. And so the idea behind liquefied natural gas is that you can liquefy the gas, that reduces the volume by 600-fold. And then once the gas is liquefied, you can move it to where it needs to be, re-vaporize it, and then send it to consumers through a pipeline at that point. And so, if you look down here, those last two bullet points we've got from 2018, the primary suppliers and the primary consumers, just think about those geographic locations, right? Qatar is the primary supplier of liquefied natural gas. They're on the other side of the world from those consumers. All of those consumers are in Asia. And so what LNG lets you do is take gas that's produced in Qatar and put it on a ship and then send it to Asia by sea. So that's the motivation here. Now, there are different plant sizes. And typically when we discuss the size of a liquefaction facility, we discuss it in terms of megatons per annum. And we've got a little table there that gives some insight into what a small plant, a medium plant, a large plant might be in terms of megatons per annum. And then just to give you a sense of scale, I've got a picture of a brand new facility here, Yamal LNG. This is a joint venture between Novatec and Total and a few other people, or well, not people, corporations. But in any case, this Yamal LNG facility that you're looking at a picture of right now, that's 16.5 megatons per annum. So this is an absolutely enormous facility. Now, when it comes to actually producing the LNG, what are we going to have to do? We're going to start with gas, right? We're going to start with gas that's coming out of a well. And we've got to think about two things. First of all, that gas is still going to need to meet our customers' needs. If we want to ultimately take this gas and put it into a pipeline for consumers or industry to use, they're going to have some specifications that we need to meet. They're going to have specifications on things like the total sulfur content, on the total water content, and on the heating value. So we may need to do some processing to get those things in line. For instance, for the heating value, we may need to do some dew pointing and remove heavy ends. The other thing is that because we're liquefying this natural gas, we're going to be operating at cryogenic temperatures. We're going to be at very, very cold temperatures. And that means that there are some considerations from the processing side of things. One of the concerns is that we could have solids form in our heat exchangers or piping. during liquefaction, again, because of those cryogenic temperatures. And so we tend to be concerned about things like the carbon dioxide content. And in fact, at the temperatures we're operating at, we can even see some hydrocarbons start to freeze out. And we'll discuss this a little bit more in just a moment. We've also got to make sure that we don't have very much water. Water could also freeze out. And there are even specifications, for instance, on this table on things like mercury. A lot of times the exchangers that we use are made out of aluminum, and mercury will attack aluminum. So there are specifications on that. Now, ProMax is really kind of the ideal tool for LNG because it does a fantastic job of helping you, perform this processing for pretty much every specification on the table. I mean, when you look at that table, the only thing that ProMax isn't going to give you really insight into is the mercury content. But we're the industry leader when it comes to acid gas processing. And so in terms of making sure that the hydrogen sulfide specification is met, ProMax is the way to go. And the same goes for meeting the carbon dioxide specification if you're using an amine plant to remove the H2S and the CO2. Now, this is a table that kind of gives the normal boiling points and normal freezing points for the components that are going to be in a gas that we may want to liquefy. And what I really want you to look at here is the freezing point. So this is the normal freezing point. And again, this is the freezing point for a pure component. In the mixture, it's going to have a different freezing point. So I'm not saying that, for instance, benzene is going to freeze out at 5.5 degrees Celsius in LNG processing. That's not what this table is trying to get across. What I want you to think about is the relative freezing point. And take a look at the bottom of the table. Those are the first components to freeze out. They've got the highest freezing points. Benzene and the xylenes, so basically the BTEX components, those are the first components to freeze out. And so they're the ones that we're going to want to pay really close attention to. That's the motivation for having that 1 ppm specification on benzene that we saw on the previous table. And in ProMax 5.0, we've actually added a tool that lets you predict solids formation point for these species, for any species in an LNG process. Now, this is a brand new feature, and it hasn't been fully integrated into the Visio part of the graphical user interface. And so right now, this tool lives in an Excel spreadsheet. And that Excel spreadsheet is located in a folder on your computer when you install ProMax. That spreadsheet for predicting the solids formation in LNG is installed in the folder that you see above. And when we actually get to the ProMax part of this webinar today, I'm going to open it and I'm going to show you how to use it. And so just keep in mind that if you have a ProMax installation, you already have this spreadsheet. It's in that folder. And then if you forget the address of that folder, it's not a big deal. You can just reach out to us and we'll be happy to help you find it. Heating value is another thing that we've got to think about when it comes to the gas. We've got to remember that ultimately this gas is going to be put into a pipeline somewhere, and they're going to have some specifications on things like the heating value or the Wabi index. If you haven't heard of the Wabi index, it's basically the gross heating value divided by the square root of the specific gravity. And it's just a really good way to discuss the interchangeability of fuels. The idea is if you have a burner that's designed for a gas that has a given Wabi index, you can use a slightly different fuel gas. As long as it's got the same Wabi index, it should work just fine. Now, today's really going to be all about liquefaction, and liquefaction is going to rely on refrigeration processes. So we've got a simple refrigeration loop here. There's basically 4 steps. We have expansion across a valve. The expansion is going to cause a huge amount of cooling, and that's due to the JT effect. And depending on the refrigerant that we're using, we may also end up going from single phase into a 2-phase region. So we may end up forming some liquid at the outlet of the JT valve. And then after that, we're going to go through an evaporator or a heater, and we're going to use that cold stream. So stream 1 is going to be very cold after expansion, and we're actually going to exchange it with what we're interested in refrigerating, evaporate our refrigerant. So In this example, the liquefied natural gas, it would be on the other side of the evaporator. It would be kind of where the duty from stream Q1 is coming. Then we take our evaporated gas, we compress it, we cool it, and then we go through another round of expansion. I mean, this is just a really basic refrigeration process. There are different types of compressors that we can use. We've got a table here that gives you some idea as to what the efficiency and turn down and maximum capacity of different compressors are. But the take home point from this slide is that the compression is really at the heart of these liquefaction processes. The compressor is what's doing the work, and the compressor is what's consuming the energy, and it's something that is going to be pretty important to us. Of course, cooling and condensing is also important. A lot of times these facilities are located on the seaside by the ocean, and so seawater is often available for cooling. And that's pretty common in large-scale facilities. And for instance, in that picture that I just showed you of Yamal LNG, there was you could see the sea in the background, right? Now, you can also use air coolers for cooling. That's fine. They do require perhaps a bit more power and they have a larger footprint, but both are used, both are possible. For the expansion step, what we're typically going to use is a valve. We're typically just going to use an expansion valve, but there are some liquefaction processes that use turbo expanders. Now, these are a little bit more, obviously a turbo expander, it's a very sophisticated piece of rotating equipment, so it's going to be more expensive than a valve. But it can be really useful if you've got a process where you don't have a refrigerant that condenses, like nitrogen. And we're going to take a look at what a nitrogen process, nitrogen liquefaction process looks like later today. Now, when we talk about our heat exchange where the liquefaction is actually occurring, the liquefaction is going to occur in the main cryogenic heat exchanger. So you may see that referred to in the examples today as the MCHE. And there are really two types of heat exchangers that we use for liquefaction of LNG, plate fin and coil wound. Plate fin heat exchangers are sometimes also called cryogenic heat exchangers or brazed aluminum heat exchangers. These exchangers have very, very large heat transfer areas. And they're typically kept in a big insulated box that is very appropriately called a cold box. And that cold box is full of some insulation like perlite and vacuum sealed. Coil wound heat exchangers are also used, and they're more common in the larger facilities. The brazed aluminum exchangers are perhaps more common in the smaller facilities, and these are pretty amazing pieces of equipment. They're expensive, they're very big, but they're really impressive feats of engineering. And I mean, I think if you just look at that picture, this is pretty cool. These are pretty cool things, pretty cool exchangers. You know, the bullet point up there points out that you can have 24 kilometers of tubing, which is just you know, incredible. So anyway, we're gonna do our liquefaction in the main cryogenic heat exchanger, and then after we've produced our LNG, we've got to store it somewhere. So we've got a storage tank here. We're going to store the LNG at very low pressure, almost at atmospheric pressure, in an insulated storage tank. And there's going to be some boil off because we will, you know, there's a huge temperature differential between this fluid and the outside air and ground. It is insulated, of course, but we're still going to have some boil off. But that's okay because, you know, we need that boil off gas to use for perhaps driving the compressors or fuel gas anyway. And then finally, we're going to have shipping. So these are just some ships that are used for transporting LNG. You can see there's different ways that you can design the tank. In the ship on the right, we've got spherical tanks. On the tank on the left, we've got more of a cube shape for the tanks. And when it comes to our actual liquefaction process, there are a number of different options available to us, and different options have different relative efficiencies. So we've kind of got this relative energy column, and the idea here is this is the relative amount of compressor energy that is consumed to liquefy some amount of gas. And what we see is that the single and dual expander processes, those top two rows, and those both refer to nitrogen, by the way, nitrogen processes. Those have a relatively high energy consumption. They're not very efficient. On the other hand, we've got down on the bottom this dual mixed refrigerant or propane pre-cooled mixed refrigerant processes, and these are very, very efficient. Now, the difference is notice that in the train capacity column, what we see is that the larger the plant, the larger the facility, the more efficient. And the trade-off that we're missing here is that these extremely efficient processes are much more complicated. Clearly, from a capital perspective, they require more equipment, more piping. And so basically the idea is that for very small facilities, it's usually better to have a slightly less efficient process that has a lower capital cost. But for very, very large facilities, the improvements in efficiency, outweigh the disadvantages of having more equipment and more piping. One of the things that we've got to ask ourselves before we start any process simulation is, what should we use as our thermodynamic package? And for liquefied natural gas, or for LNG, our instinct is probably to start by using a cubic equation of state like Peng-Robinson or SRK. I mean, those are very good for gas processing applications. The only caveat is that Peng-Robinson and SRK, we are kind of used to using them for normal gas processing at higher temperatures. And the question is, how well do they do at the cryogenic temperatures that we're dealing with LNG? Well, one equation of state that we could perhaps compare them to is GERG, which is an equation of state developed by the European Gas Research Group. And we call it on this slide a super equation of state. And to be honest with you, I don't really fully understand the implementation myself. What I understand is that GERG is heavily based on experimental data and functions almost like a steam table where it's more of a lookup from experimental data. So if you look down on the bottom, we give you the list of components that are compatible with this equation of state. It's not a completely general equation of state like Peng-Robinson or SRK. If you look at those species that work for GERG, we see basically everything we would need for liquefied natural gas, methane through propane, oxygen, water, carbon monoxide, carbon dioxide, etc. And so GERG is a really good way to go. And we can use GERG, in fact, when we're simulating a liquefaction process. On the right here, we've given you the heat capacity for a gas stream. And we're showing you GERG, Lee Kessler, Peng-Robinson, and SRK. And the idea here is that you can kind of take GERG as the reference. You can consider GERG to be more or less the truth. And so then the question is, how far do the other equations of state deviate from the GERG curve? And you can see they all do a reasonably good job. Peng-Robinson and SRK both do a very good job. Notice that Peng-Robinson does a slightly better job than SRK at very low temperatures. And then as we warm up a little bit, SRK at some point does a better job than Peng-Robinson. Here's another plot that shows you GERG versus Peng-Robinson, SRK, and Lee Kessler. And this is a parity plot for vapor pressure of some natural gas stream. Experimental data versus the calculated data. And again, we see that GERG is the way to go, but that you can get good results with Peng-Robinson or SRK. And perhaps what you're asking yourself right now is, why not simply use GERG for all of our calculations? There are two reasons that you may want to use one of the cubic equations of state instead. The first is that GERG is a bit slower. It's faster to do flash calculations in Peng-Robinson or SRK. So one approach that people will take sometimes is to do the bulk of their simulation work in Peng-Robinson When you work in simulation, it's a very iterative process. A lot of times you're experimenting, you're trying out new ideas, and you want things to go fast because the faster you can simulate, the better your iterative problem solving is. So it's good to use Penn Robinson or SRK for that. But then what you can do is when you get close to what you feel like is your final result, you can switch over to GERG and then get those really accurate granular results. The other limitation with GERG is that it's missing a component that we actually use a lot in LNG. Take a look at those components in the lower left-hand corner that are supported for GERG. If you can figure out what GERG is missing, let me know in the chat. I'll give you a few seconds to think about it. There's one component that's very important in LNG liquefaction that's missing. Do you know what it is? Benzene? Yeah. So June posted benzene. That's right. Benzene's missing, and benzene's very important. Ramon posted CH4 methane. Methane's actually there, Ramon. If you look, when we say C1 through C3, C1 would be methane, ethane, and propane. Okay, I've got other people saying benzene. Yeah, so benzene is a big problem. And then actually, to be honest with you all, when I said one component, I actually had a different one in mind, and I'm really happy that you guys mentioned benzene. And I've got a private message from someone saying helium, which is also true and is often present. The one that I was thinking of was actually ethylene. Now, ethylene is not something that we're going to have probably in our gas that we want to liquefy, but a lot of times we want to use ethylene as a refrigerant. And so if we've got ethylene as a refrigerant, that also makes things with GERG a little bit tricky. So there are some good reasons that we would want to use one of the equations of state. And what we're going to kind of default to for the liquefaction here, I think, is at least in the examples that I showed you today, is Penn Robinson. And if you look at how close Penn Robinson tracks the GERG, again, at low temperatures, it makes good sense to use it. Okay, so here's the first process that I wanted to show you today. This is a cascade refrigeration process. And the idea here is that we are going to use multiple different refrigerants. And in this case, what we're using is propane. That's the C3, that's the smallest inner loop. Ethylene, we're indicating that with C2 equal sign, where the equal sign represents that double bond between the carbons. Methane, we're using methane as our final stage of refrigeration to get us to our really cold temperature. Now, why do we, the first question is, why do we need multiple different refrigerants? And then the second question is, how did we choose these refrigerants? Well, the reason we need multiple refrigerants is simple. If you think about propane refrigeration system, we couldn't liquefy natural gas using pure propane as a refrigerant, right? Because the coldest that we can get pure propane is about -35, -40 degrees Celsius, somewhere in that range. For LNG, the temperature that we're typically trying to target is about -155 degrees Celsius. And generally, we prefer to perform liquefaction at a high pressure. That makes our piping a lot smaller, right? If we're at a high pressure, we've got higher density, we can have smaller piping. So notice that we've got this LNG expansion valve. So typically, some common temperatures, and basically what we're going to use in all of the examples that I show you today, the temperature in stream 4, which is just upstream of that expansion valve, that is going to be at about -155 degrees Celsius. And then the temperature in stream 5, which is just downstream of the expansion valve, that's going to be something below -155, maybe -158, -160. The actual temperature that we end up with there is kind of going to depend on the composition of the gas and the pressure that we flashed here. Let's take a look at this table of cascade refrigerants, and this is kind of comparing different possibilities for us. And let's think about this from the outside in. And when I say outside in, I mean, let's think about the coldest refrigerant first, which is methane. Why are we using methane here as our coldest refrigerant? Well, take a look at this first column, the boiling point, and notice that methane's boiling point at 1 bar, which is basically where we're going to be operating. Remember, we want to get really cold by expanding across a valve, and We don't want to expand to vacuum, so expanding to about 1 bar is pretty reasonable. So with methane, we can get down to a temperature of about negative 162 degrees Celsius. And if our goal is to hit negative 155, like we discussed before the LNG expansion, it seems like methane can get us there. Now, notice that nitrogen can also get us there. Nitrogen's boiling point is negative 196. So we could also produce LNG with nitrogen. One disadvantage, perhaps, of using nitrogen is that nitrogen's still going to be in the gas phase. And that means that we have to do everything in the gas phase. We don't have any liquid refrigerant in a nitrogen system. So that means that we're going to have bigger piping, and it means that we don't get to take advantage of latent heat. All of the cooling has to be done with sensible heat. So methane perhaps is a little bit more attractive to us because it can get us to the temperatures that we want, and it can actually work as a liquid refrigerant, which has a lot of benefits. Now, the next question is, how do we get methane to liquefy? Now, if we want methane to condense, we're going to have to drop below its critical temperature, right? Now, remember that we're talking about pure components here, right? So there's no phase envelope. If you imagine like, the pressure temperature plot for methane, the dew point, bubble point line, it's a single line, right? So to get to the liquid region, we've got to drop below the critical temperature, which is negative 83. So we need a refrigerant that can do that. And obviously propane, which again is going to get us down to negative 40 or so, is not going to be adequate. We need something that can get colder. So two good things, or two good proposals, would be ethane and ethylene. If you look at ethane's boiling point, it's negative 88. Ethylene is negative 104. So both ethane and ethylene, since they have boiling points at negative 88 and negative 104, they could be conceivably used to liquefy the methane refrigerant. Now, which one do we choose? Well, again, we think about that methane critical temperature, we've got to drop below, it's negative 83. Ethane's boiling point's negative 88, and so there's not a big overlap there. There's not a very big safety margin. So a lot of times what we want to do is use ethylene. Ethylene's boiling point's negative 104. That gives us about 20 degrees of difference between methane's critical point, ethylene's boiling point. So ethylene is really probably the preferable choice in this case. And again, that's just because it kind of gives us a bigger safety margin than using ethane, a little bit more flexibility. But how do we get the ethylene into a liquid form? Well, for that we can use propane. And since we considered ethane and ethylene, why don't we consider propane and propylene? Here, we don't see such a dramatic difference necessarily between the critical temperature and the boiling point overlap as before. And there's another problem, which is availability on site. If you kind of imagine, we discussed that we're going to have to do some gas processing, dew point control, before we can actually liquefy this gas, right? And so it's very easy to imagine there being a gas processing plant with a fractionation train somewhere reasonably close to where our liquefaction facility is, right? Wherever those liquids from the gases are removed. So there's probably a very convenient source of propane available to us, and ethane for that matter, perhaps. For propylene and ethylene, that's not true. There's not necessarily going to be, an ethylene cracker near our liquefaction facility. So what we're going to have to do is we're going to actually have to purchase that ethylene and then bring it on site and store it and manage it. And it's worthwhile for ethylene, but for propylene, typically it's not really worthwhile to deal with that. We'd rather just use pure regular propane, which is available and common. So anyway, that's the motivation for using propane, ethane, and methane. And then if you think about what the cooling curve for this is going to look like, on the left plot, that red line, that's the natural gas. And the way to think about this is the sections that have steeper slopes, those really represent the sensible cooling. And then the flatter sections where it's more isothermal in nature, that's really where the liquefaction is occurring. we can also create a composite curve where we put all of the heating and cooling curves together, because remember, we're going to have actually 3 curves, one for each refrigerant. And so that's shown on the right. And I'm going to show you how to actually create one of those composite curves in ProMax in just a moment. Now, the other option that we have is the mixed refrigerant process. So the idea behind the mixed refrigerant process is that rather than having multiple different refrigeration loops with methane and then ethylene and propane, we can actually just create a mixture of methane, ethylene, propane, butane, and then have a single loop. And what that's going to do is it's going to give us a refrigerant curve that is no longer just a flat line. And we're actually going to be able to get the heating and cooling curves to line up with each other. So, if I go back to the previous slide here, you can see that we've got the blue dashed line that represents our propane, our green dashed line that represents our ethylene, and then our yellow line that represents our methane. But here, for the mixed refrigerant process, we're able to just track our cooling curve exactly. And that's by maintaining, and that's by designing the system with the correct mixed refrigerant composition, and then maintaining that composition throughout operation. The advantages of having a mixed refrigerant process are that we've got higher efficiency. We get those heating and cooling curves really close together. We've got lower equipment cost because we only need one set of compressors instead of 3. But there are some challenges. It's difficult to maintain the composition, and if we need to use something like a coil wound heat exchanger for this, that can introduce some problems for us. But this is basically what a mixed refrigerant process would look like, and you can see this is much simpler looking than that Cascade process. And typically, this is going to be used for smaller facilities, less than 1.5 megatons per annum. And finally, I've got a picture of the nitrogen cycle here, and this is a lot like the single mixed refrigeration process, right? We've just got a single refrigeration loop. Nitrogen's our only refrigerant, and that means that we've got one heat exchanger. So we get that benefit, and then we also get the benefit of the Cascade processes, which is that we only have one refrigerant to worry about. We've just got pure nitrogen to worry about. And nitrogen is something that's very easily available. It's in the air around us. I'm sitting in a bath of nitrogen right now, so you can produce your own nitrogen and use that to load your charge in the refrigeration loop. The difficulty or the problem perhaps here is that, like I showed you on that table earlier, the nitrogen cycle is just not very efficient. And one of the reasons for that is because it's kind of hard to get those cooling curves close together. With our mixed refrigerant process, we've got a lot of control over the heating and cooling curves. We can take the curve that the refrigerants represent, we can tune the refrigerant composition to get those curves really close together. But with nitrogen, we don't have that flexibility, right? Nitrogen's curve is just going to be a straight line, or well, yeah, it's a straight line of constant slope because it's just sensible heating. There's no latent heat involved. And so because those curves are so far apart at some places, the process ends up being less efficient. Now, there are ways to overcome that. You can use something like this dual expander configuration where we have a warm expander and a cold expander. And in that case, you end up with 2 curves for nitrogen. And here we've managed to get these curves a little bit closer together, but you can still see that there are some areas where the curves are quite far apart. So we're going to take a look at all of these in ProMax now and see what it actually looks like when we get to simulation. So the first thing I want to show you, I've got a blank ProMax project here, and I'm just going to open an LNG example. We've got a huge library of built-in examples that are always available for you to reference, and they're also available for you to modify, and they're good starting points for your own simulation work. So I want to show you how to get to those. I'm going to go up here to File, and then I'm going to click on ProMax. And from here, I can click Open Example Project, and this is going to open our examples library. And In the example I'm going to look at, I'm going to go into the folder midstream. And then in midstream, I'm going to go into the LNG folder. And you can see we've got several different examples here. We're going to be looking just at these examples today. The first one I'm going to show you is this LNG Cascade process. Let's open that up. First of all, I'll help get you oriented. We've got our feed here. So this is going to be our gas stream that we'd like to liquefy. You can see that we've got a flow rate of 1 megaton per annum. We're coming in at 50 bar and 40 degrees Celsius. And if I open this up, we can just take a quick look at the composition. And you see that we've got 88% methane, 7% ethane, 3% propane, a bit of butane, and some nitrogen. And what we do is we go through multiple different exchangers, getting cooler and cooler each time. So we go through our propane chiller. That takes us down to 17.7 degrees Celsius. We go through a second propane chiller. That takes us down to negative 7.63. We go through a third propane chiller. That takes us down to negative 32.4. We continue on through 2 different ethylene chillers. That gets us down to negative 96. Finally, we go through 2 methane chillers, 3 methane chillers. We get to a final temperature of negative 155 degrees Celsius. And then we flash down to our final storage pressure of 1.4 bar. That's absolute. You can see that that ends up, if I open that stream, vaporizing just a little bit. So there's about a 3.3% end flash here. And our final temperature is about negative 158 degrees Celsius. Now, this is a lot more complicated than what I showed you on the slide. And the reason for that is because we're actually using economizers in our refrigeration loops. And in fact, here in our propane refrigeration loop, we have 2 different economizers. So it's pretty common on simple propane refrigeration skids to have 1 economizer. Here we actually have 2. And if you're not familiar with what economizers do in refrigeration processes, the idea is that we're mostly interested in using the latent heat of this refrigerant. So the actual refrigeration process occurs isothermally at 1 temperature, whatever temperature we expand the gas to, because we expand the refrigerant. As we expand it, it's going to liquefy, and then we're going to extract the latent heat from the liquid, but that all occurs at constant temperature. And the idea here is that because we know we have to recompress, we don't really want to spend energy compressing refrigerant that doesn't get used for cooling. So rather than drop or expand to a very low pressure and then have to recompress some of the gas that never got used for refrigeration, we expand to an intermediate pressure. We take the gas that forms at that intermediate pressure, we send that to an intermediate stage in our compression system, and then we only use the liquid. And here we're actually expanding to 2 intermediate pressures. We're expanding to 7.5 bar, which drops us down to 15.7 degrees Celsius. Again, this is for propane. And for 3.5 to 3.5 bar, which drops us down to negative 9 degrees Celsius. And then finally to 1.4 bar, which drops us down to negative 34.4 degrees Celsius. We set the exchangers up based on approach temperatures. And what we're assuming here is that we have a cryogenic heat exchanger. So this would be, for example, one of those brazed aluminum heat exchangers. And we'll assume that we can get a very good approach temperature, perhaps 2 degrees. And we've configured this model to have 2-degree end approaches. Let's just take a look at the first propane chiller and see what I mean. If we open this up, and then I go to the Process Data tab, and then I click here on Heat Transfer, you can see that we've got a minimum end approach temperature of 2 degrees Celsius. And let's take a look at the plot for this exchanger and see what that looks like. I'm going to click here on Heat Transfer, which is going to show me the 2 curves together. And I can see that, indeed, I've got that 2-degree approach on the cold side. The propane, our actual refrigerant that's entering the system, it's here in stream 303. And its temperature, 15.7 degrees Celsius, that's entirely a function of the pressure that we expand to. We've chosen to expand to 7.5 bar. And I know that because there's an asterisk here in this callout. The asterisk indicates to me that the user has defined that value. In fact, if I open this stream, you'll see that the pressure is here in blue. Again, in ProMax, blue indicates that the user has defined this value. And the temperature is just a result of the expansion. So we end up at 15.6 degrees Celsius here, 15.7 degrees Celsius. And then to get our 2-degree approach, what we do is we set the temperatures in each of these outlet streams to be 17.7 degrees Celsius. So we assume that we get that 2-degree approach. And just to zoom out so that you understand what all of those streams are, one of those streams is the feed, which is being chilled, but then we're also chilling our methane refrigerant and our ethane refrigerant or ethylene refrigerant. The way that we set these temperatures up is using simple specifiers, which are a type of calculator in ProMax that can set one value based on the value of something else. So if I open stream 202, and by the way, the reason that I can immediately tell and know that these are set using a calculator is because there's this hash mark or hashtag, pound sign, whatever you want to say. That, when I see that pound sign on a call out, what that indicates to me is that a calculator is setting this value. And indeed, if I open this stream, if I open stream 202, I see that there's a solid blue background under the temperature, which is another clue that a calculator is here. When I right click on this value, if I click show calculator, number one, that's available to me because the background is blue. There's a calculator installed. And if I look at what this is doing, what this calculator does is it takes a look at this independent variable, C3 chiller 1 temperature natural gas. And if I hover over it, I see that a pop-up come out. So this is a local reference to the temperature of stream 2. You can see that in the call out or in the pop-up that comes up. So basically what this calculator is doing is saying, set the temperature of this stream, stream 202, equal to the temperature of stream 2. Similarly, if I open stream 102 and I look under its temperature field, I'll right click again and click show calculator. Again, we have the same reference. It's referencing stream 2. So I have a calculator on stream 202's temperature that sets it equal to the temperature of stream 2. Calculator on stream 102's temperature, which sets it equal to stream 2. And then if I open stream 2 and I right click at its temperature and look, here I've got this set up a little bit different. The variable here in stream 2, it's actually taking a look at stream 303's temperature. So if I hover over this, you can see that this is pointing to stream 303's temperature. And then what we do is we add our desired approach to that value, set that as the temperature for stream. And now this whole system is fully automated. And I could do something, for instance, like instead of expanding to 7.5 bar, if I were to expand simply to 8 bar instead, all of those temperatures would update for me automatically, and I would still have my 2-degree approach. So you can see now, when we expand to 8 bar, we're getting to 18 degrees Celsius here, and these temperatures have all updated automatically. So once you set those specifiers up on your outlet temperatures on your heat exchanger, everything is handled for you automatically, based in this case on what we've set as the expansion pressure here. Now, what if we wanted to look at the complete grand composite curve? I mean, I showed you the composite curve for this individual exchanger when I opened it and I went to the plots tab. But what if I wanted to see all of those curves overlaid on each other? We've got a lot of exchangers here. We've got 8 different exchangers. Well, we have a tool for that. It's located in what we call our property stencils. Basically, these property stencils are tools that run on top of ProMax and execute some scripts that we've written. And we've written a stencil that produces the grand composite curve for this exchanger. Now, I'll go ahead and load that. I'm going to click here on More Shapes, and I'm going to click on Open Stencil. And And then I need to navigate to where I have my composite stencils. So I'm going to go to just the folder where I've got this stored. So just bear with me for a moment here. Um, I've got this folder that's holding this compound heat stencil. And this stencil is again available, something that's available to you if you request it for us. In this case, this stencil does not ship with ProMax, but we can supply it to you if you request it. So I'm going to open that. And when I drag this compound heat stencil out onto the flow sheet, a pop-up is going to appear, and it's going to ask me which exchangers I'd like to include in the plot. And I would like to include all of them, so I will select all of them and click OK. And here we go. Here's our composite exchanger curve. I can see for each one of those exchangers, I can see what my curve looks like. And you can kind of get the idea. Again, I've mentioned this briefly before. One of the things that's going to really affect the efficiency of this process, the closer we can get those heating and cooling curves together, the more efficient our process is going to be. And by breaking our refrigeration loops up into multiple steps, so for instance, having 3 stages of propane refrigeration or 3 stages of methane refrigeration, it helps us kind of squeeze those curves closer together. So that's how you do a grand composite curve. This is what a cascade refrigeration process looks like. We're not going to go into too much more detail on this because, again, the whole idea today is to just kind of give you a general survey of what's possible in ProMax. Let's take a look now at a mixed refrigerant process. Oh, no, actually, there was one more thing that I wanted to show you here, and that was the LNG Solids Excel spreadsheet that I mentioned earlier. I've got that spreadsheet open here. This is what that spreadsheet looks like when you open it. There's a set of instructions over here on the right, but it's really easy to use. All we have to do is specify our property package, our temperature in units of Kelvin, our pressure here in units of bar, and then the composition. Right now, I don't have anything in here for the composition. So let's go ahead and I'm going to open my feed stream and let's take the values from that feed stream and put them into this calculator. So I have 88% methane, 7% ethane, 3% propane, 0.5% of each of the butanes, and then 1% nitrogen. And I'm going to go ahead now, the way that this spreadsheet is set up, it's not set to calculate automatically because the calculations can be fairly computationally intensive. So we're using a feature that I didn't actually know about in Excel until I started using this spreadsheet. In Excel, if you click on the formulas ribbon, there's this section here where you can set the calculation options. And we've actually set the calculation to manual for this Excel spreadsheet. And what that means is that when you enter values into Excel, they don't update automatically, which is the behavior that we normally expect. So to get this to run, I actually need to click this Calculate Now button. So that's what I'm going to do. But first, I want to go ahead and set my temperature and pressure to be correct. We said that we were trying to get to about negative 155 degrees Celsius. And in fact, we said the end flash was negative 158. So I'm going to set the temperature here to negative 158 for our end flash. And I'm going to click Calculate Now. And what this does is it calculates the fugacity ratios for a solid phase, a hypothetical solid phase for each component. And then it's going to tell us if it predicts the presence of solids. And so here, what we see is that the maximum fugacity ratio for any of our given components is 0.69. And again, that's the fugacity ratio with respect to the phase that's present and the hypothetical solid phase. And so if it's less than 1, we won't have solids form. If it's equal to 1 or greater than 1, we will have solids form. So let's try to add something that would potentially cause solids. Let's try to add benzene. And I'm going to propose that we add about 100 ppm of benzene. Now, when we do that, what we're going to have to do is make sure that our composition still sums up to 100. So if I were to come down here to benzene, and I were to add, for instance, I'll put in benzene as 0.01 mole percent, my molar composition now actually is not going to be equal to 100 anymore. It still says 100, but remember that it only says 100 because the spreadsheet's not calculating automatically. So this actually right now sums up to 100.01, and I've got two options here. I could normalize this. That would be okay. Or I could just use methane, our biggest component, as kind of a balancing component. So I could say the methane is actually equal to perhaps 88% minus however much benzene we have. And then this is always going to sum to be 100%. And I can kind of start to tweak and play with the amount of benzene. So if I had 100 ppm benzene and I click that Calculate Now button, aha, look at this. We're being told that the maximum fugacity ratio is 15.9, that solids will form, so we've got this red warning, and if I go down here and I look at where the solids form, I see, indeed, it is for benzene. Benzene is the problem. I've got this plot worksheet that I can go to, and this is actually going to show me the fugacity ratio for benzene over the full temperature range here. And I can see that benzene is, and this is actually kind of interesting. You can see, if you're able to see my mouse over here on the left, here we're going to have benzene formation, and then we're going to have benzene formation here, and then we've kind of got this weird region in here where, like, if we're cooling from here, we start with no solid benzene, we go to the left, and then suddenly solid benzene starts forming here. We'll have solid benzene all the way down to here. That's at about 195 Kelvin, and then it disappears for a little while, but then it reappears. But in any case, the temperatures that we're working with, it would be a problem. And actually, that plot, it comes from this table. So this table is basically showing you for each degree Kelvin that we're at. We've got degrees Celsius here as well. If we go down to where we were at, we're trying to get to negative 158, and the fugacity ratio there is 16. So we've got solid benzene. So that plot is basically just generated from this table, and you can generate this table for any component that you want to. You can just choose the component to generate the table for from this list. And that's how this tool works. It's really useful. There's other stuff that you can do with this. If you wanted to, for instance, figure out what the minimum amount of benzene would need to be before, I kind of got tripped up on my words there, but what I was trying to get at is, if you wanted to figure out, what's the smallest amount of benzene that I could have that would cause a problem, you could start, for instance, adjusting this benzene fraction. I could say, okay, well, if 100 gives me solids, what if I went to 50 ppm? And again, I'm just going to come up here to formulas and click Calculate Now, and I see 50 ppm. I've still got solid benzene, and this will actually work with the Excel solver. So I could run solver, for instance, and I could say, you know what, set the objective cell, the max fugacity ratio, equal to a value of 1 by adjusting, for instance, the benzene constant, or the benzene concentration, subject to the constraint that it's greater than 0. And if I click solve here now, and we just let the Excel solver run for a moment, it should pretty quickly find for us exactly how much benzene would cause a problem at negative 158 degrees Celsius, 1.4 bar. Okay, so it's at about 6 ppm. That's the result here. So I've got you can see solver says it's converged to a solution. So 6 ppm benzene. So now that kind of makes that 1 ppm benzene specification we saw on the table before seem pretty reasonable, right? And you could do the same thing that I just showed you. You could put a solver on the temperature to show you what temperature solids would form for a given concentration. So anyway, you have this tool installed on your computer if you've got ProMax installed, and we'll be happy to help you use it and support you with it if you need to. So this is something that's really, really useful. And I just want to point out also that in ProMax, if you've ever used us for like gas processing, you should know that ProMax is always checking for solids formation in streams, in pipelines, and in columns. It's looking for dry ice, it's looking for frozen CO2, it's looking for hydrate, it's looking for solid water. And ProMax will issue warnings about all those things. ProMax itself, in the Visio GUI, will not issue you a warning about the potential for having frozen benzene. So that's something that you've got to check yourself using that Excel spreadsheet I just showed you. Okay, that's it for the Cascade refrigeration. Let's take a look at another process. I'm going to go back to File. I'm going to click on ProMax, and I'm going to open another one of our examples. And I'm going to open, again, our midstream folder, LNG. And now let's take a look at that single mixed refrigerant cycle. Let's take a look at what a mixed refrigerant process would look like in ProMax. This is much simpler, agreed? We've just got, a single refrigeration loop, and that means that, it's capital-wise much simpler. Again, the feed, it's 1 megaton per annum. We're using the same gas here as we were in the previous example, 88% methane, 7% ethane, etc. And we're going down to the same end flash, negative 155 degrees Celsius at our high pressure, and then end flashing down to 1.4 bar, which gets us a temperature of negative 158. And we've set this up a little bit just like before. Notice here that on the cold side, we are basically assuming a 3-degree approach. So after expansion, our refrigeration achieves a temperature, or our refrigerant gets to a temperature of negative 158, and it's kind of cooling itself here. This is auto refrigeration, and then this is the refrigeration of the LNG. So we have a 3-degree approach on the cold side, and then on the warm side, we've also got a 3-degree approach. We're not explicitly showing that right now, but if I were to copy and paste this call out to show you the temperatures here, we're at 40 degrees Celsius. Our refrigerant, after compression, it's coming into the exchanger at 40 degrees Celsius, and then it's leaving at 37 degrees Celsius, okay? And the way that we've actually set that up in this simulation is a little bit interesting. We are using what we call a solver to set the flow rate of the refrigerant. Now, in the previous example on the Cascade refrigeration page, I didn't explicitly discuss this, but the flow rates of all of the refrigerants were set by the duty requirement. And here it's a little bit different. Here what we're doing is we're setting the flow rate of refrigerant here in stream 101. And I know that, again, because I see the flow rate here and I see that hash mark. So we're setting the flow rate in stream 101 such that stream 104's temperature is 37 degrees. And we're doing that because that gives us a 3-degree end approach here on the hot side. Now, just to prove to you that I've got that 2-degree approach and 3-degree approach, let's open the heat exchanger itself and go to the plots tab. And here I see that I've got that on the cold side, I've got that 2-degree approach, or 3-degree approach rather, and I've got a 3-degree approach here on the cold side. And notice how this curve is really pinched up right against the other curve. It follows it pretty closely. And that's really beneficial from a perspective of efficiency. How did we actually achieve that? If I open stream 101, that's where we've set the composition. If I click on composition here, this is the mixed refrigerant we're using. It's a mixture of methane, ethane, propane, butane, and nitrogen. And let's take a look at how we set up the flow rate. Again, if I look at the flow rate here, it's 4.6 megatons per annum. How did I get that value? Well, the solid blue background, that's my clue that there's a calculator at work here. And before, what I showed you was a calculator called a specifier. That was for the Cascade process. Here, we're actually using a calculator called a solver. The difference is that the solver is actually an iterative calculator. It's kind of going to use a guess and check method. And so if I open this up, what it's doing is it's taking a look. We've got local variables here. We're looking at the temperature of the feed stream and then the temperature of stream 104. So those are our 2 local variables that we use in this solver. Again, that's just the temperature of the feed, which is 40 degrees Celsius, and the temperature of stream 104. And what we want to do is we want to have those two temperatures be within 3 degrees of each other. We want an approach of 3 degrees. So we've got this expression up here. The temperature of the feed, which is 40 degrees Celsius, minus the temperature of stream 104, which is currently 37, divided by 3 minus 1. And this is perhaps a little bit mysterious until it's explained to you that what the solver does is run a root finding algorithm. And as a root finding algorithm, what it's going to do is it's going to try to adjust whatever it was installed on. In this case, it was installed on the refrigerant flow rate. It's going to adjust the refrigerant flow rate until it finds the root for the expression that we've written in this box. And the way that we've set this expression up is such that the root will occur when the approach is equal to 3 degrees. And this is going to be an end approach. So that's how this works. And then let's do an experiment here. Let's say that you're an engineer, or let's say that I'm an engineer, and I'm responsible for creating a simulation of a process that's actually running. Let's say that this gas composition that's in here now, let's say that this is the design composition, but loading these systems is actually not trivial. It's not easy to actually get this charge in there at the exact composition. So let's say that they just tried to load this up and that the actual composition deviated a bit from the design composition. So I'm going to change this composition. And let's just pretend that even though this was what we designed for, what really ended up in there was 30% methane and then 32% butane. So we've got a little bit too much butane, not quite as much methane. And this is just a simple thought experiment. So we'll leave the ethane, the propane, and the nitrogen the same. See what happens. Now, I've still got that solver in place. So that solver is still going to try to get me those approach temperatures. And that means that the flow rate's going to change a bit. All right, so the flow rate dropped down to 3.9. I do still have my 40 degrees Celsius here and 37 degrees here, so I'm still achieving my end approach temperature. But now the exchanger's yellow. Yellow is always something that you need to watch out for in ProMax. Yellow is like a caution flag. It's telling you to take a look at the warnings, take a look at the message log. And if I look down here at the bottom in the message log, I can see I've got this warning saying that exchanger 100 contains a negative or close endpoint or internal approach temperature. Rating is not possible. Let's open it up and see what's happening. If I look at my supply and demand curve plot, I see I've actually got a pinch in the middle now. So even though I've got a good end approach temperature here and a good end approach temperature here, there's an internal pinch, and that's why I've got this yellow block, and it's a problem. Now this is thermodynamically impossible, so we need to do something to fix this. We've got to get rid of this. And one thing that we might do is, instead of controlling the refrigerant flow rate such that we get the end approach temperatures to be 3 degrees, what if we controlled it such that we got the effective approach temperature to be 3 degrees? So I'll show you how we could set that up. I'll go back to my refrigerant stream where we've set the flow rate in stream 101, and I'm going to go back into the solver. And now what I'm going to do is I'm going to come up here and I'm going to put 2 forward slashes in front of the original expression. That creates a comment. And so now, because I've got those 2 forward slashes, ProMax is just going to ignore anything that it sees on this line. And I'm going to create a new line. And I'm going to write down here effective approach minus 3. So again, this is a root finding algorithm. It's going to find the root when the effective approach is equal to 3. If I write here effective approach minus 3. And I'm going to now go down to my measured variables and click add. And I just need to create a local variable that represents the effective approach. So I'm going to open my flow. This is my property moniker tree, and I'm just going to navigate to that block, the main cryogenic heat exchanger. So that's exchanger 100 here. And then the effective approach can be found here in this Q manager section. And so I'll just click here on maximum, or rather minimum effective approach temperature. I'll give that the same name that I wrote in the expression above, EFF approach, effective approach. And now, if I solve this, it's green now. Now I no longer have a 3-degree end approach. I've got 40 degrees Celsius here for the feed, and I've got 15.6 degrees Celsius here. So that end approach is no longer good, but now I've eliminated that temperature cross. So this is something that's really useful, is to use a solver to try to get the effective approaches to line up if you've got an internal pinch, and that can be really important when you're doing these mixed refrigerant processes. Okay. So that's kind of what I wanted to show you for the SMR, and I just want to show you one more process now. I want to take a quick look at the nitrogen process. And I want you to keep something in mind here. And actually, I'll go ahead and I'm going to open a new instance of ProMax to do this. Note that the power that we're using here is 40 megawatts. And that's perhaps not optimal because we kind of made a change, composition, and we assumed that we had a mistake. But regardless of that, we're at 40 megawatts. Let's open an example of a nitrogen process for this exact same gas and see what kind of energy consumption it uses. So again, I'm going to go to midstream, LNG, and I'm going to open this LNG nitrogen expander cycles example. And again, you have all of these examples yourself. These come with any ProMax installation. And here is a LNG nitrogen single expander cycle process. And note here that the total power consumption is 78.8 megawatts. And this is for the same gas. Again, we're doing that same gas, 1 megaton per annum. So this is clearly a less efficient process. And just a couple things I want to point out to you. We're using an expander here. And because we're using an expander, we can perform an isentropic flash rather than isenthalpic. Valves do isenthalpic flashes. So that's what we're doing with the previous examples. Here we've got an actual expander, and that means that we also have this booster compressor that we can use, and we get to cooler temperatures. But even though we're at negative 158 here, we're still in the gas phase. If I open stream 158, you can see that this is fully in the vapor phase. And the explanation for why the power consumption is so much higher here is really simple. Let's just open up that supply and demand curve. We'll go here to plots, heat transfer. And you see we've got this huge gap, right? So this is really why we've got such an enormous duty. It's just not efficient to extract heat like this. Now I can show you I've got that dual expander process here. So here we're actually going to use a warm expander and a cool expander. This is slightly more complicated in terms of how to set this up. And again, the refrigerant here, this is just pure nitrogen. But by going to 2 stages, we've managed to go down to 50 megawatts. So, and if you remember, our SMR was 40 megawatts. So now we're actually kind of starting to get competitive with the SMR. I can open this exchanger and show you the plot. And you can see here that the reason, again, for the efficiency improvement, we've managed to really get these 2 curves closer together. And we could play, for instance, with the different temperatures, that this point right here where the slope changes, that's basically the temperature that we're operating. One of these curves is from the cold expander, and one of these curves is from the warm expander. And we could, if we wanted to, kind of move around where this temperature occurred, or we could move where this point occurred at by changing the temperatures that we operate at. But again, here you got to be careful, because you can imagine if we just went straight up like this, we could have an internal pinch. So that's something that can potentially be limiting here, is that because now we've got this change in slope at this specific point, we could have an internal pinch. But that's the nitrogen process, and we don't have too much more time left today, so we'll just talk about one more thing. I just want to show you the difference between Peng-Robinson and GERG in this case. So right now, if I click up here on active environment, I can see that the equation of state that I'm using is Peng-Robinson, okay? And here's the question. What would the difference be if I used GERG? Well, let's get some benchmarks first. I'm going to click Clear Calculations here, and then I'm going to click Execute Flowsheet. And the reason I'm doing that, I want to see how long it takes for this to solve with Peng-Robinson. So I see that it takes 2 minutes and 55 seconds to solve with Peng-Robinson, and that my total power is 49.2 megawatts. And I'm just going to make a little text box here that has that as a note. I'm going to say with Peng Robinson, it was 2.55 seconds to solve, and I got 49.2 megawatts of power. Now let's go over to GERG and see what happens. So I'm going to click here on ProMax, go to Active Environment, and I'm going to change the package I'm using to GERG 2008 Equation of State. We'll click OK. And I'm going to solve this twice. I'm going to click Execute Flowsheet once, and this solve is going to take a little bit longer because we have some solvers set up on the flowsheet, and because GERG is just a little bit different, it has to reiterate. So now I've kind of gotten to a solved state, and now my question is, from a solved state, how long does this take to solve? I'm not sure if that makes sense, but really I'm just trying to get this to be apples to apples. So now I'm at the same place I was earlier when I did the timing benchmark for the Peng-Robinson equation of state. So now I'm going to do execute flowsheet again, and let's see how long this takes. So 3 minutes, or 3 seconds, 3.14 seconds. So that's actually not bad, 3.14 seconds to solve. So, we say in our slides and sometimes in our courses that GERG is a little bit slower, but the truth is, practically speaking, it's not that much slower. So you could probably, for especially something simple like this, just work in GERG full time. And then if you notice the duty, though, we're talking about 49.2 megawatts for Peng Robinson, 50.1 megawatts for GERG. So not a huge difference. GERG definitely, if you can use it, I would say there's no reason not to. But if you need to use a cubic equation of state, they're going to give you pretty good results too. And that's all we've got for you today. So I hope you enjoyed this lecture. We've got about 10 minutes for questions. And so I'm going to be looking at the chat. And if you guys have any questions, I'll be really happy to answer them. Okay, there's a question. How do you go about choosing interstage pressure and flow rate for a multi-stage refrigerant cycle? Where is the refrigerant flow specified? That's a good question. Let me go ahead and reopen. I shouldn't have closed it, but that's okay. I'm gonna reopen the Cascade Refrigerant process, and I'll show you how that's done. So the interstage pressure choices, those are going to be kind of arbitrary. One of the things that you've got to think about is how your compressor actually works. So, typically you want to have a compression ratio in the range of 2 to 3, and can't have really, really high compression ratios, right? So you kind of got to balance the compression ratios from each of your stages. But if you're doing that, you still have a little bit of flexibility, and it is a bit arbitrary. And really what you would want to do, I suppose, if you were designing the process, you would want to probably iterate over different potential interstage pressures and see which one was the most efficient. So, for instance, in this process right now, if I look at my total energy consumption, I should have that on the flow sheet somewhere. Right now, the power my propane system is consuming is 14.4 megawatts, okay? So let's just see what happens if we change one of our interstage pressures. We did our first expansion at 7.5 bar, and then what I did earlier was I changed this to 8 bar. So this is a small change, and I'm not sure if we're going to see a difference in the power consumption, but let's just try it. I haven't rehearsed this, but remember that previously the power consumption from the propane compressors was 14.4 bar. And now at that higher expansion, well, it's still 14.4. We don't have enough significant figures here to see which direction it's changing in. But I tell you what, why don't we just, this is coming in at 13.8 bar. Maybe we can do something like, we'll expand to 12 bar. Again, these answers to questions are not rehearsed, but I hope it kind of gives you guys an idea of how I go about using the simulator to answer questions. Okay, so now I see that my propane power here is 15.7 megawatts, right? So basically, in terms of choosing those interstage pressures, what we're really interested in doing, it's minimizing our compressor power. And here, raising that first expansion from 7.5 to 8, it didn't make a big difference. But then when I went from 8 to 12, now I'm consuming a full extra megawatt of power. So it's really just an optimization problem. And then in terms of the flow rate, the way we've actually set this up, I didn't have time to explain this fully, but we're using a very special block here called the propagation terminal. And this is used when we have systems like a refrigeration loop where the process fluid is being recycled, but there are no losses or basically the system is closed. It's used for closed loops. And what this does, this entire propane refrigeration loop is going to solve simultaneously algebraically. And the flow rate, in this case, this is actually being calculated automatically based on the duty. Now, we know what the duty is because it's the duty that we need to cool these three streams. For each of these three streams, we know what temperature they are coming in, we know their composition and therefore their heat capacity and everything like that, and we know the outlet temperatures. So basically, we calculate the duty based on what it takes to get these three streams down to 36 degrees Celsius, and then ProMax figures out that to satisfy that duty, we need a given flow rate. In this case, 10,000 kilograms per hour. But the flow rate's determined automatically based on the duty. So I hope that answers your question clearly. If that wasn't crystal clear, just let me know and I'll be happy to clarify. I've got another question. Is the feed gas composition of the LNG process the overhead stream from the demethanizer of an NPL process? Yes, that would be right, Hussein. You would use your demethanizer overhead for this. Basically, it's just going to be, LNG is gas that's pipeline specification gas, right? That's kind of the idea. It's just that instead of transporting it in a pipeline, and so basically it should be ready for consumers to use. It's just that instead of transporting it in a pipeline, we're going to have this intermediate transportation step where we liquefy it and then move it as a liquid. There's another question. Is there any insight into how the effective mean temperature difference moves as the MR composition changes for SMR? Yeah, we can go ahead and open our SMR and we can take a look at that. And this is one of the things that having ProMax available to you is fantastic for. If you kind of want to develop an intuitive sense of, for instance, how this heating and cooling curve is going to change as you change the composition of the mixed refrigerant, you can just do experiments, right? It's free to do experiments in a process simulator. So let's take a look at this curve right now, and I'm going to go ahead. I'll take a snip from it with the snipping tool. So this is what we've got. And now let's make some changes to the mixed refrigerant composition and compare it. So let's maybe go back to where we were before. So instead of having this 32% normal butane, let's take that back down to 27, and then take our methane back up to 35. And then we can resolve this, and then we can compare the two curves. Okay, so the curve on the left is the one with 35% methane, 27% butane. And then I'm going to load that snip back onto the screen. The curve on the right is with more butane and less methane. And you can see that the big difference that I see here is that this section is smaller. And you can see that we've kind of shifted things around here just a little bit. But this is something that basically I can't even imagine designing a mixed refrigerant process without something like ProMax. When you've got ProMax, you can just try lots of different compositions and then really get a sense of how the system behaves and get those curves close together. So I hope that was useful. Honestly, if you're really curious about this, I would encourage you to just open up this example just like I've got. You've got access to the same example and play with the composition just like I'm showing you. Yeah, okay, I've got a question. Can we see what the actual volume change was from the feed to the final product? Sure. So if I open up the feed stream here, I go to the properties. Let's take a look at what the volume was. Now, I'm interested in the actual volume. So that's this, not the standard volume or the normal volume, but the actual volume. The actual volume flow, it was 2,889 cubic meters per hour in the feed gas. And then the LNG it's reduced to 237 cubic meters per hour. So in this case, it's a volume reduction of about 100. When we said 600 earlier, that's obviously going to depend on the pressure that you're operating at. Here, the feed was at 50 bar. If that feed was at 1.4 bar, the same pressure as the LNG, so I made a copy of that feed stream. This is the feed. I'm going to drop the pressure here to 1.4 bar. The vapor volumetric flow goes up to 115. So that would be, we can go ahead and calculate the ratio here. That would be 114, 155 over, I can't remember what the LNG was, 200, 237. So at atmospheric pressure, in this case, the volume reduction is about 482. Yeah, and then good point. The 600 is probably for pure methane. So it's a little bit different here for this gas mixture, but still in the neighborhood of 600. Same has asked, is any pre-treatment required? And the answer to that is yes. I mean, like we discussed in the slides, very often pre-treatment is required to make sure that the heating value is correct, to make sure that we don't have CO2, to make sure that we don't have water, to make sure that we don't have benzene. But in the examples that I've shown you today, we haven't touched on pre-treating because we're assuming that the feed has already been treated. Now, if you didn't need to do that pre-treating, ProMax is a great tool for that. I could just show you an example. For instance, if I go to here to the midstream gas processing folder, I can show you, for example, a GSP plant example. This would be a demethanizer that we would be using to do some pre-processing. I could show you amine, sweetening examples. So I suppose the answer, Hussein, is yes, you're almost always going to require some pre-treating. We didn't touch on it today, but you can use ProMax for all those different pre-treating processes. So here, for instance, Hussein, here's a simulation of a demethanizer. So this would perhaps be some pre-treating that we could do before going to our LNG liquefaction train. Okay, I'm gonna go ahead. We'll conclude for today. If you have any other questions, feel free to just email me or Václav or Katrina, and we'll be happy to answer your questions. And thank you guys for your attendance and your attention. We really appreciate you attending these webinars. We hope that you enjoy them. We certainly enjoy preparing them and teaching them. It's really rewarding and nice for us. So I wish you an excellent rest of your day, a good week, and I hope to see you at future webinars and trainings.